In lesson 37, they introduce the idea of defining the line as a locus of points. And this is a good introduction because when we talk about circles and ellipses and hyperbolas later on in the course, each of those can be defined as a locus of points. So first of all, let's think about the word locus. The kids and I are learning Latin this year, and locus means, like, if you can kind of almost see the word location, that the locus is the Latin root of the English word location. And you can think of that, it means place or location. Okay, so when we talk about a locus of points, it's kind of like a set of points, but it's all the locations that satisfy some kind of constraints that you put on it. So the definition that they give us for a line is this. A line is the locus of points in a plane that are equidistant from two specified points. My black marker's running out. Okay, so if you think about that, okay, we have this important thing, there's two specified points. Let's say we have point A and we have point B. So those are our two specified points. And so a line is every possible point, a collection of all the possible points whose location is exactly equidistant from those two. So imagine if I were to like draw a straight line between them, maybe that's like right in the middle. So that is equidistant from A and B. But there's lots of other points that are also equidistant from A and B. So maybe a point over here, if I were to measure out this way and back that way, that looks like about equidistant. And let's see, let's say if I went out this way and that way, that looks about equidistant. And I could also go this direction, and I can get a whole bunch of different points, and all of those are equidistant. So if I were to measure from B to this point and come around and do A to that point, they should be equal. And you can see that I'm going to get this big collection of points, and they're all going to lie in this straight line. Like this. So there's an infinite number of those points that are equidistant from A and B, and if we put all of those points together, we will get a line. So that is all the locations that are exactly the same distance from A and B. So that is our definition of a line using the locus definition. Okay, now that is helpful when we have problems like example 37.2, where it says we need to find the equation of the line that is equidistant from the points 4, 2, and -2, -3. And we need to write that equation in slope-intercept form. So really what we have is basically the same picture, but this is like 0.42 and this B is like -23. So we know that there's some line that's equidistant between or equidistant from those 2 points. So how exactly would we find the equation of that line? So let's just start by drawing a little picture. I like pictures. Okay, so we have 1, 2, 3, 4, 1, 2. This is 0.42. And we have -2, -3. Okay, so there's lots of these points, okay, but we're just going to pick one of them. Let's say this one, and we'll call this x, y. It has some coordinate. We don't know what the coordinates are at this point, but we know that it's the same distance from 4, 2, and from -2, -3. There's lots of other points on this line. Let's say it kind of looks like this. So I could pick any point XY on that line. And after I pick that line, I know that if I were to draw this segment right here, this distance, I'll call this distance number 1, would be exactly the same as this distance right here, and I'll call this distance number 2. Okay, so the distance D1, well, that's just the distance from point -2, -3 to the point XY. So we can put that in the distance formula and figure out what that is. Okay, so the distance formula, we have to take the differences of the x. Since these are negatives, I'm just going to go ahead and start with x. So it would be x minus -2, or x plus 2 squared. And then y minus -3, or y plus 3 squared. So that would be the distance D1. The distance D2 we can find in a similar manner. So we would have x minus 4 squared plus y minus 2 squared. Okay. Now we know, because this point is on this line that's equidistant, that D1 have to be equal to D2, so we can just set these two things equal to each other, and we should be able to come up with an equation for the line from that. Okay, so we have distance D1, which is x plus 2 squared plus y plus 3 squared. Will have to be exactly the same as distance D2, which is the square root of x minus 4 squared plus y minus 2 squared. Okay, so we'll square both sides, and then we'll just get x plus 2 squared plus y plus 3 squared is x minus 4 squared plus y minus 2 squared. And let's go ahead now and just expand these and see what we can get rid of and make our life a little bit easier. So first of all, we'll go ahead and square the x plus 2, so that's x squared plus 4x plus 4. And we'll expand the y plus 3 squared, that will be y squared plus 6y plus 9. We'll expand the y minus 4 squared, so that will be x squared minus 8x plus 16. And finally square the y minus 2, so we'll get y squared minus 4y plus 4. Okay, so if we subtract x squared from both sides, those will go away. If we subtract y squared from both sides, those will go away. If we subtract 4 from both sides, those will go away. I don't have to deal with those anymore. Okay, since we want the equation in slope-intercept form, let's put all of the y's on the left-hand side and all of the x's and all of the constants on the right-hand side. Okay, so we'll leave the 6y here. And then we also had, okay, so I've taken care of that one. And now we also had this negative 4y. To move it on the other side, we need to add 4y. So we've taken care of that one. Okay. So now we need to move the x's to the other side. So we'll move this to the other side by subtracting 4x. We've taken care of that. We still have then a minus 8x. Okay, I need to subtract 9 to get this on the other side, and I still have this plus 16, and I believe that should take care of all my terms. Yes, I've done it correctly. Okay, so this gives us 10y equals negative 12x plus 7. Okay, and then if we divide both sides by 10, we will get y equals negative 12 tenths x plus 7 tenths, or if we reduce that fraction, we will get y is negative 6/5 x plus 7 tenths. Okay, so that should be the equation that's equidistant from the given points in slope-intercept form. Okay, so now that we're good at that, let's just go ahead and do another one. But this time we've got two different points. And what you might want to do, what I would suggest, is why don't you go ahead and stop the video now, see if you can go through the process that I just went through and find the equation for yourself, and then you can just fast forward through my solution and make sure you did it just like I did, and check that. That would be my suggestion. If you don't feel like doing that, you could always just watch me do it, but it's more exciting if you solve it yourself. Alright, so once again, we'll just kind of draw ourselves a little picture here. Okay, we have 0, negative 4, and we have 5, 2. And we want to find the line that is equidistant, so imagine it probably goes something like that. And so we'll just pick some random point x, y. So I need to calculate this distance right here and this distance right here and set them equal to one another. Okay, this is point 0, negative 4, and this is 5, 2. Okay, so let's go ahead and do this distance first. So that distance will be the square root of x minus 0 squared plus y plus 4 squared. And then we'll calculate this distance over here. That will be the square root of x minus 5 squared plus y minus 2 squared. Okay. So if we square both sides, the square root symbols will go away. And let's just go ahead and expand these out as well, so we don't have to run out of space on my paper, and I had to write so tiny on the last one. Okay, so this x minus 0 squared is just x squared. The y plus 4 squared will be y squared plus 8y plus 16. The y minus 5 squared will be x squared minus 10x plus 25. And the y minus 2 squared will be y squared minus 4y plus 4. Okay, so if we subtract x squared from both sides, those go away. If we subtract y squared from both sides, those will go away. Okay. And so let's get all the y's on the left-hand side. So we'll have 8y from that, and we'll have to add 4y to move that one over. That takes care of all the y's, and so we're left with negative 10x. And then we need to subtract the 16 to move that over to the right. And we have the positive 4, and that should take care of, oops, and we have a positive 25. Alright, that's why I cross them out, to make sure I don't forget anything. Okay, so this leaves us with 12y equals negative 10x. Alright, and then this would be negative 12, and so that would be plus 13. Alright, and dividing both sides by 12, we get y is negative 10 twelfths x plus 13 twelfths. And if we reduce that, we get negative 5 6x plus 13 twelfths. And after you get your equation, we should have done this last time, but it's probably always a good idea to look at maybe the example line you drew and see if it makes sense. So do I have a y-intercept around 13/12? Well, in my picture it's just above 1, so that seems reasonable. And is the slope looking like it might be something like -5/6? Well, let's see. If I started here, did I go down 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5, 6? Yeah, it looks pretty close. Okay. So it's usually good to give yourself a reality check. If you had ended up with a positive slope on this line or something, you would know that you did something wrong. So the picture is often a good double check. Okay. So the next thing that we want to do is review the midpoint formula. But before we do that, let's just do a little bit of review. So a few lessons ago we talked about finding a point that's 5/6 of the way between, you know, x1 and x2, something like that. So if you think about the midpoint, this is just a special case of that kind of problem. The midpoint is exactly halfway between x1 and x2. Now, when we did those problems, we discovered that you have some kind of directed distance, and it mattered if you said, well, what's 5/6 of the way between x1 and x2, where x1 is the start and x2 is the finish. That would be different than 5/6 of the way between x2 and x1, where x2 is the start and x1 is the finish. We're going to go ahead, hopefully it's somewhat obvious to you that if doesn't matter what my directed distance is, whether you start at x1 and go to x2, or you start at x2 and x1, you should probably end up, and if you're doing halfway between, you should end up at the same place. But let's go ahead and derive the general, with just using variables, what that spot would be, and see what we get. So first of all, let's look at, you know, halfway from x1 to x2. Okay, so we would start at our initial point, which is x1, and we would add on half the distance from x1 to x2. And the way that we find that distance is we take the terminal point, x2, and subtract the initial point, x1. And that should give us the point that's exactly between x1 and x2. Okay, so let's find a common denominator of 2. This would be 2x1 over 2, and then distribute this half, and we'll get x2 over 2 minus x1 over 2. Okay, so we have two x1s minus an x1, which leaves us with just an x1. Then we have the plus x2 all over 2. So the point that's halfway between x1 and x2 is x1 plus x2 over 2. And let's just go ahead and verify that if this were our initial point and this were our terminal point, we'd still get the same thing. Okay, so half the distance, or halfway, the point that's halfway from x2 to x1. So again, we start at our initial point, x2, and we add on half the distance. So how do we find the distance? Well, we go to the terminal point, x1, and we subtract the initial point, x2. Okay, so you can see that this is looking very similar to the previous one. We'll get 2x2 over 2 plus x1 over 2 minus x2 over 2. When we do x2, 2x2 minus x2, we'll just get x2. And we still have our x1. And so, of course, if we rearrange this, use the commutative property of addition, we can rewrite this as x1 plus x2 over 2. So it doesn't matter what the terminal and what the initial are. You always get, the way that you find the midpoint is to add the two x values and divide by 2. Okay, Now hopefully this is ringing some bells and you remember that we did this in geometry, and I think we even reviewed this in Algebra 2. Okay, so that's for a number line, but how do we then take this and extend it to just two general points? Let's say this is x1, y1, and this is the point x2, y2. And I want to find the point that's exactly halfway in between. Now, if you recall, find the midpoint. The x-coordinate of that midpoint would be x1 plus x2 over 2. And the y-coordinate of that would be y1 plus y2 over 2. Okay. So if you think about, going back to our discussion about this, okay, so if there were a number line between the x1 and x2, it would be exactly halfway between those, and if there were a number line between y1 and y2, it would be halfway between those. So let's just convince you that that is actually a good way to find the midpoint. So if you think about, let's kind of just extend a parallel line over here and extend one down here and kind of connect the 2 points. Okay, so this line that's going through x1 is parallel to the x-axis, and I'm going to draw another line that's parallel to the x-axis here, and another one that's parallel to the x-axis that goes through x2. So if you recall, I think somewhere near the beginning of the book we looked at a theorem. We even looked at a proof of it that said if you have parallel lines and we have some transversals that go through those parallel lines that are intersected by those parallel lines, that the proportion of the segments cut off by the parallel lines on one transversal will be exactly the same proportion as the segments cut off on another transversal. So if I can look at this transversal right here, which happens to be perpendicular, okay, and if I can find, so here, for this point right here, that would have a y-coordinate of y1. And this point would have a y-coordinate of y2. Right, so this point right here would have a y-coordinate of y1 plus y2 over 2, because it's on this just one-dimensional line between there. I don't know what the x-coordinate is. I don't care what the x-coordinate is right now. I just know that halfway between there, that would be proportional. Now, if that y-coordinate will divide this into two equal segments, then that same y-coordinate will divide this into two equal segments, because we've got these parallel lines in this transversal, and we know that this has to be cut in the same proportions as that one. Alright, and then we can use a similar kind of argument going in this direction. Okay, so the x-coordinate here, okay, so I'm just going to put a blank for the x-coordinate here. I don't care what the y-coordinate is on this one. I just wanting to look at the x-coordinate. So the x-coordinate will be halfway between the x-coordinate here, which is x1, and the x-coordinate here, which is x2. Okay, so that point halfway between those two would be x1 plus x2 over 2. I don't care what the y-coordinate is. Okay, and we know because that's exactly halfway between there, then anything going through this same point right here would have to proportionally cut this. Since these are half and these are half, these ones also have to be half. So if I just use this x coordinate that proportionally cuts this leg in half, and I use the y coordinate that proportionally cuts this in half, I can guarantee that that point will be one that cuts this hypotenuse in half. Okay, so that should hopefully, it's not a rigorous proof, but it is hopefully an argument that convinces you that that midpoint formula actually works and it actually is true, and that there's a logical reason as to coming up with that. Okay, so we'll just finish up by doing a simple little midpoint formula calculation. So what is the point halfway, or the midpoint, between -2, 6 and 4, -10? And we might not need a picture, but just in case you accidentally subtract instead of add or something, it's not a bad idea to go ahead and draw yourself a picture and check your reality. 1, 2, 3, 4, 5, 6. Okay, so that's -2, 6, and 4, 1, 2, 3, 4, -10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then halfway in between, I'm going to say, is about right somewhere in here. Okay, so the midpoint, the x coordinate should be adding the two x coordinates and dividing by 2. And the y coordinate should be adding the two y coordinates and dividing by 2. Okay, so this will give us 2/2, which is 1. And this gives us -4/2, which is -2. Okay, 1, -2. I was okay. I'll make a really big X and pretend I was a little bit more accurate. Okay, so 1, -2. It should have been right there. Should have been our midpoint. I think this scale is kind of poor. All right, but at least if I got, you know, a +2, 1, +2, and it was up here, we was that's not too good. That's not very close. So at least it was close enough that I could see that I must have used the midpoint formula correctly. Okay, so that should do it for lesson 37. And let me know if you have any questions.